Hi, welcome back. Today's lesson is on microcontroller timers and counters. And this is sort of a two-for-one deal because I'm going to teach you about timers, and once you learn about timers, counters work exactly the same. So you get two lessons for the price of one today. Timers and counters can be used for a variety of applications. Timing how long it takes for an event to occur, counting parts as they pass through an assembly line, setting up time delays and things like that. We use them in a lot of applications, so be sure to understand how to program and work with these devices. And like most concepts in the electronics field, this material doesn't come easily. So you have to read it, look at the diagrams, plug in ones and zeros, make a serious effort to understand what's being described. So if at any point you don't understand something, don't skip it and move on. Read it again, play with the information, redraw the diagrams, ask questions. Okay? Reading technical material isn't like reading a novel. Watching instructional videos like this is not like sitting back and watching cute cats on YouTube. You can't just sit here and veg out in front of the screen. You have to think about things and become actively engaged with the material. Okay? So think hard about this. Microcontrollers, as we know, have a great deal of flexibility. These timers can be configured in a lot of ways for different applications. In order to configure them, you program them by writing to a control register. Now, if you saw my lesson on analog to digital converters, you already know about programming control registers. The PIC timers have a control register for each timer, and each register has certain bits that do a particular function. Okay, we'll see this in all kinds of microcontroller features. The control register is a very common feature of microcontrollers, so we touched on it a little bit with analog to digital converters, and we're going to see it again with programmable timers and a lot of other programmable peripherals that go with microcontrollers. So before we look at the PIC timer counters, let's take a little review about ripple counters, okay, or what you should remember from your digital electronics class. So you're looking at a 3-bit ripple counter. Each flip-flop represents 1 bit. And it has a clock pulse coming in, and the counter will count each clock pulse that comes through. Okay, so its initial value, it's going to start out with all zeros. So we have 0, 0, 0 out of the ripple counter. When we get a clock pulse that comes in, first clock pulse that comes in here is going to cause the ripple counter to count up to 1. Okay, what happens on the next clock pulse? Well, the next clock pulse causes this to go to 0, and the count rolls over, and now we get 0, 1, 0. That's binary 2. Okay. If I pulse again, I'm going to get a 3. If I pulse again, I'm going to get a 4. Let's fast forward a little bit until I pulse a 7th time, in which case I get 1, 1, 1. That's the binary equivalent of the number 7. So now the question is, what happens on the 8th clock pulse? Well, in a regular ripple counter, on the 8th clock pulse, the counter just rolls over to 0. And that's how our timer counters work as well. The counter will roll over to 0. If we had an extra bit, then let's call it an overflow bit, it would be a 1 right now. And that's really just a 4th bit attached to here. Okay? So if that's a 1, that would indicate that, hey, the other 3 bits overflowed. We ran out of room and we had an overflow. That's going to be important later on because we do need to know whether this timer has timed out. Now, a microcontroller's timers are usually 8 or 16 bits. The PIC controller has a 16-bit timer counter. Just think, if I showed you a 16-bit timer and went through every possible combination of ones and zeros, this would be one really long video. So aren't you glad I gave a 3-bit example instead? So let's take a look at some applications of timers and counters. Okay, we'll start with timers. Well, for one thing, microcontrollers are really, really fast. They operate on a very fast clock signal, usually like 20 megahertz. I know that doesn't sound fast if you're used to a 3 gigahertz processor in your PC, but for a microcontroller, 20 megahertz is still quite fast, and that's 20 million things per second, much faster than a human being. So a lot of times if you want to slow something down, let's say you want to make a light blink, an LED blink, if you just write a 1 and a 0 to that LED, it's going to blink so fast that there's no way a human being is going to catch that. So we quite often use time delays to slow things down so that the microcontroller really just sits there and kills time waiting for the slow human being to catch up. Okay, we might also want to time how long how long it is between 2 events. So how long does it take for 2 events to occur? How long in between them? And for counters, Okay, one of the more common applications for counters are electronic turnstiles. If you've been to a concert or a sporting event, you might have gone through the turnstile. That's a big thing that turns the wheel, that counts how many people have gone in. Okay, they can happen electronically as well. And on an assembly line, we often have to count parts that go down an assembly line. After 24 parts go by, it wants to do something else. So we can use counters for that application as well. Timers versus counters. Well, like I said before, they operate almost identically. Okay, here's the only significant difference is that timers increment on CPU clock pulses. So that clock pulse that we saw coming into the ripple counter on one of the first slides, the CPU clock is what comes into a timer. Okay, remember that the CPU clock is what keeps all the data flow inside the CPU synchronized. So it's kind of like the metronome for a musician or the drummer in a band. It keeps everything in sync. So timers increment on CPU clock pulses. Counters will increment on external pulses. That means you put an external signal in. So for example, if I wanted to count parts coming down an assembly line, I might have a sensor that pulses every time a part goes by, and that would go into our counter. That would feed the clock pulses for the counter. But other than that, a timer and a counter operate exactly the same. So let's take a look at the PIC timer counters. Well, to begin with, this PIC chip, the 16F877A, has 3 programmable timer counters. They're called Timer 0, Timer 1, and Timer 2. Timer 0 is an 8-bit timer counter. Timers 1 and 2 are 16-bit timer counters, and their operation is identical to each other, so I'm just going to show you Timer 1. And each one has several modes of operation, and you choose the mode based on the control word that you write to its control register. So, okay. Here's the diagram, the block diagram for Timer 1. Now I know it looks complicated, okay? But hey, it's like a big sandwich. Don't try to eat it all at once. Take one bite at a time. Process that, go on to the next part, okay? So the individual parts are not as complicated as the whole picture looks. So let's look at it one little chunk at a time. Okay, let's start with the heart of the timer itself, and that is the timer register. Okay, this is a 16-bit register. Now remember that the PIC microcontroller is an 8-bit CPU, so we usually only deal with 8-bit registers. So we can think of it as a 16-bit timer, as Timer 1, TMR1, okay? But we also can think of it as 2 8-bit registers that are put back to back. So that's Timer 1 high, that's the high byte of Timer 1, and Timer 1 low is the low byte of Timer 1. So when we say Timer 1, TMR1, I'm referring to the entire 16 bits. If I say TMR1H, that's the high byte, TMR1L is the low byte. Okay, remember I talked about what happens if the timer times out, which means that it goes from all ones and then you get one more clock pulse in. Well, it rolls over to all zeros, and then the flag, the overflow flag, will be a 1. Okay, so there's a bit in a register somewhere, it's in one of the control registers actually, called the TMR1IF. Okay, make sure you spell that correctly in software. TMR1IF, that's a capital I, capital F. It's the Timer 1 interrupt flag, and I'm going to call it an overflow flag because it makes more sense. Okay, when the overflow flag is set to a 1, that means that the timer counter has rolled over or timed out. That means that this went from all ones to all zeros. And we can test that bit with an if statement, or the timer can generate an interrupt. For now, we'll just test it. You can either use an if statement or you can use a while loop, just kind of like we did when we were waiting for the analog to digital converter to complete a conversion. Okay, our count pulses, as I mentioned before, the difference between a timer and a counter is that a timer will count clock pulses and a counter will count external pulses. So this bit right here, the Timer 1 CS bit, is the clock select. That determines whether we are counting internal clock pulses or external pulses that come in from an external pin. Okay, this bit is in the control register, and we can write to that later on. So here, what we're seeing is I've got a 0. When it's a 0, then it's taking the FOS over 4, that's the oscillator frequency, that's the system clock frequency, divided by 4, and that's what goes into here, and that's what goes into the timer. We'll talk about the prescaler next. Okay, if this bit is a 1 in the control register, then what we're doing is we're taking a signal from an external pin, and bringing that in. Notice this pin name, it has 3 different names because it has 3 different purposes. RC0, you're already familiar with that. That's bit 0 of port C. But if we're using it as our external clock source for our counter, we can't use it as a general purpose port bit. Okay, so this would be the T1 clock signal if we were using it for that purpose. The prescaler is used to divide that clock down by 1, 2, 4, or 8 before it gets to the timer itself. When you need long time delays, even though this will automatically cut the clock frequency by 4 before it feeds into here, even that might not be enough. It might not slow it down enough, so we can scale it down even that much more. So for your maximum, you're already dividing it by 4. If I divide it by another 8, well, 8 times 4, that means it's dividing the whole thing by 32. Okay, and I have 2 bits in the control register that tell whether I'm doing a divide by 1, 2, 4, or 8. Okay, there's a bit in the control register called the timer 1 on bit. Okay, and that just turns the timer on or off. It doesn't actually turn power on or off. What it does is it allows clock pulses to come through. Okay, remember how an AND gate operates. You can use this sort of to allow this signal to go through. What I'm doing here is, with this bit, if this bit is a 0, if you've got a 0 on one pin of an AND gate, what is the output? The output will always be 0 regardless of what's going on here. So if this is a 0, basically it's turning the timer off. It's saying, I don't care if clock pulses are coming in, they're not getting out, and they're not reaching the timer. When this bit is a 1, every time you get a pulse here, that pulse will come over here. Now, here's the timer 1 control register. Okay, notice, hey, there's only 6 bits, much easier than the analog to digital, which actually had 2 full 8-bit registers. We only have 6 bits to worry about here. Okay, these 2 are unused. So let's take a look at them. Whoops, sorry. Okay, these are my clock prescaler. So bits 5 and 4 are my prescaler. So remember, I have 1, 2, 4, or 8. So you would have 0, 0, 0, 1, 1, 0, or 1, 1. Okay, these 2 bits we're not going to concern ourselves with. We're just going to leave them as zeros. If you want to know the details about that, you can consult the PIC manual. Okay, we won't use these in our applications. Okay, this one is the timer 1 clock select. This defines whether it's a timer or a counter. And this is what turns the timer on or off. So, to put it all together. Okay, the timer 1 CS bit is what programs it to be a timer if it's a 0 or a counter if it's a 1. By the way, if you're using it as a timer, what you're going to do is load an initial value into timer 1 high and timer 1 low. That starts counting from that value. If you're using it as a counter, you're probably going to load 0 into those 2 registers and then just let it count up. Okay, the timer 1 on bit turns the timer counter on or off, so it enables the clock pulses to get in or disables them, blocks them. When the timer rolls over to 0, its overflow flag will be set. Okay, remember the lesson on analog to digital converters showed you a little while loop that waits for a bit to be a 0. In this case, you'd be waiting for the bit to be a 1, but the while loop would be almost exactly the same. And if you're using this as a counter, what you would do is check the read the timer 1H and timer 1L registers to see how many pulses it has counted. So there you have it, enough information to get started using the PIC microcontroller's timer counters. Okay, so I hope you found this lesson to be a productive use of your time. Bye.